So what do you say we close out this chapter with a few examples that look like your homework problems? You and I will kind of work through these together today, and then of course next time it'll be your turn on your own when you do the homework set. I have a lot of files going on, so I think it's going to be easier for you if you have some of these printed and in front of you. I'm going to be working through the problems on this worksheet, sampling distribution examples, which comes at the end of the sections 6.3 to 6.5 illustrations and examples handout. So this is the handout that starts with your table of statistics and parameters up here. Oh yeah, I should have just clicked on the contents here. I also will be working a little bit with the sections 6.3 to 6.5 outline. I have that one printed in front of me, and I'd recommend that you have it printed and in front of you too. I'm going to close that one on my computer screen because I found that I just have too many documents to look at on the screen. So if you have that one in front of you, it'll help follow this lecture a lot more easily. But I'll be doing a couple other things on the screen. Okay, so question number 1 says, NBA players score a mean of 8.7 points per game with a standard deviation of 5.2. That 8.7 is actually pretty close to the league average. I totally made up the standard deviation. The points per game distribution is heavily skewed to the right. And that's probably actually true too, because there are a few outliers who score way more than 8.7 points per game. If I take a team of 13, which would be a typical full roster through a game, I'd like to find the probability that these 13 players will have a mean exceeding 10 points, which would place the team score over 130. So that's what I would like to find out. The question I'm presenting is, can I analyze this problem with a normal distribution? So the question basically is, since I'm working with means, is the sampling distribution of means going to have a normal shape? So I hope you remember we talked about how to analyze sampling distributions of means not too long ago. And we discussed something called the central limit theorem, which gives us information about its mean, standard deviation / standard error, and its shape. And do you remember what the conditions were for that shape to be normal? If you look at your lecture outline, you'll find that it will be a normal shape as long as one of the following conditions applies. If the parent population has a normal shape, or if the sample is large, meaning at least 30. So let's go through these requirements one at a time. Is the parent population normally distributed? And do you remember what we said about that distribution up here? We actually said the points per game distribution is heavily skewed to the right. Aha. That's not normal. Normal is symmetric. Okay. So for that reason, no, the population does not have a normal shape. Okay, so let's try the other condition. We wouldn't need the parent population to be normal if the sample is large. Large means at least 30. What about this sample size? Uh-oh. Team of 13. That's a small sample. Okay, so therefore we have to conclude that the answer to this question is no. I cannot analyze this problem with a normal distribution because neither one of these conditions is met. So that's what those rules are for. Therefore, that's the end of problem 1. Okay? Solving that problem would basically be beyond the scope of this course. It's like, well, if it's not normal, then I don't really know what to do with it. So let's move on to problem number 2. Pet store mice. I've been an avid mouse keeper for a decade now. I actually get my mice from breeders now, but I've gotten many in pet stores. All right, so pet store mice have an average lifespan of 1.2 years. That's pretty close to the average, actually, with a standard deviation of 0.4 years. I take 3 mice home from the pet store, and I'd like to know the probability that their average lifespan will be more than 1.5 years. So before we dive into a problem like this, we really have to make that language connection. We need to be making the connection between the plain English and the technical terms with their appropriate symbols. Okay, that's basically one of the biggest challenges in this class for many students. So I call it turning numbers into letters. So for example, we see a 1.2 up here, we see a 0.4, and there are some other numbers in this paragraph. And I want to actually pause the video for a while and have you think about this first. So I would like you to practice figuring out exactly which symbol represents each one of these numbers. And what I'll do is I'll give you 5 seconds to pause the video and then think about it. And then when you unpause, I'll present the answers here. All right, so we're basically able to summarize this whole paragraph with these few representations. That's the challenge, but also the power of abstraction, right? Because it doesn't, at this point you can see these symbols, they don't say anything about mice or lifespans. It doesn't really matter what they represent anymore. But what we do need to understand is what each of them represents in a mathematical sense. So this 1.2 is the average or the mean of all pet store mice in the whole wide world. Therefore, since it's a population mean, that is symbolized by mu. Mu equals 1.2. And that population has a standard deviation of 0.4, which is given the symbol sigma. I take 3 mice home. That's the sample size. Lowercase n equals 3. And then to restate the question, the probability that the mean of these 3 mice, the sample mean, will exceed 1.5. Right? So the population mean is 1.2. That's for all the pet store mice in the whole wide world. The x bar is just the mean of these 3 mice that I take home. That's the difference between a sample and the population. I want to find out what's the probability that these 3 little creatures will live to be an average of more than 1.5 years. So part B of the question says, do I have enough information to know whether I can analyze this problem with the normal distribution? Well, that's very similar to question 1, isn't it? Okay, so let's see. Let me sort of copy and paste that part down here. Okay, so is this population normally distributed? What did this paragraph say about that, if anything? Pet store mice have an average lifespan of 1.2 years. That's the mean, with a standard deviation of 0.4 years. That's the spread. But we always need to know 3 things about a distribution. Mean, center, spread, and shape. I don't see anything about the shape yet. Nope, not there. I don't know. Is the population normal? Unknown. Or is the sample size large? No, it's only 3. Okay, so the answer to this question is, do I have enough information? No, I don't have enough information yet. But look at part C. Okay, so here, not enough information. Part C, though, says, now, what if I told you that the distribution of pet store mice lifespans is normal? Ah, got it. Okay, so in that case, we could go up here and say the population is normal. Yes. Okay, then we're good to go. All right, then the question continues, what could you tell me about the sampling distribution of means for samples of size 3? Okay. So first of all, so basically we're characterizing the sampling distribution, and remember we need 3 pieces of information for that: center, spread, and shape. So since the parent population is normal, doesn't that tell us that the sampling distribution of means is also normal? Right? That was discussed in this handout up above when we talked about sampling distribution of means. The central limit theorem says the sampling distribution of means is normal as long as the parent population is normal. Okay, so there we go. Okay, so what about the center and spread? And let me jump back up here again. Oh, here they are. There's formulas for them. All right, so let me just copy these. 2C, okay. I'll paste them here. And I will basically plug in the information that we have. Okay, so the mean of the sample means is the mean of the population. That's 1.2, isn't it? Okay. So your typical sample of 3 mice will live an average of 1.2 years. And the standard error of those sample means has this little formula. So let's plug the numbers in here. And that's why it's so essential to turn numbers into letters at the beginning of the problem, right? Because we know that we need mu, sigma, and n, and that's why we wrote them down up above. Okay, so now we know what numbers to plug into the formulas. So into this formula, we're plugging in sigma and n. Here they are. We already wrote them down, 0.4 and 3. So when we plug those numbers in, we get 0.4 over the square root of 3. And I believe I already calculated that. And this is something you can do on any calculator. I'm getting a decimal approximation of about 0.2309. Part D, what are the z-score, percentile, and p-value for my chosen sample mean? In other words, 1.5 was the mean I was looking for. So let me copy that here. I'll just copy all this again. All right, so I've pasted the essential information here. We're looking for the probability that the mean is above 1.5, given that the mean is 1.2, and the standard error is 0.2309. So the first part of the question is z-score. So this is something, have we done this before? Yes and no. This is what we've done before. This was the the z-score formula when we were working with the parent population, right? Now, in this problem, we are working for the first time with a sampling distribution of means. So we just have to, have to specify what exactly is being measured on this distribution. So remember that the sampling distribution of means measures sample means, x bar. So instead of calling this x, we're going to call that variable x bar. And its mean is symbolized by the mu x bar, mean of all the sample means. And its standard deviation is symbolized by standard error. I distorted that before. Which is abbreviated as sigma x bar, right? The standard deviation of all the sample means. So I'm just basically putting these 3 versions of those variables into the formula now. So on the sampling distribution of means, the z-score gets symbolized this way, right? We are going to take our sample mean of interest and subtract the mean of all the sample means, and then divide it by the standard deviation of all the sample means, aka the standard error. And again, we have all those numbers on hand. Here they are. So these are the numbers that we will now plug into the formula. So when I plug those numbers in, 1.5 for my sample mean, 1.2 for the population mean, and 0.2309 for that standard error. We can calculate this very easily, and it gives us a z-score of 1.3.